This video will investigate translating between position, velocity, and acceleration graphs. Let's begin by looking at a simple situation where an object starts at the origin and moves in the positive direction. We see that this shows up on our graph as a straight line, diagonal line, where the slope is equal to the rise over the run, or delta x over delta t, which previously we have defined as the average velocity, which in this particular case is 12 meters over 3 seconds, or 4 meters per second. Notice that if we were to look at this graph, every second that passes, the object is moving 4 meters. So this represents a constant velocity. We can take the slope at any point to find the velocity at that point. If it is not constant or diagonal line, we would be looking at the slope of a tangent line, as I will discuss later. What would this constant speed of 4 meters per second look like on the velocity versus time graph? What we see is just a straight line across a horizontal line at 4 meters per second. Now, let's consider the slope of the velocity versus time graph is the rise over the run, which is delta v over delta t. And again, previously we've thought about this idea as the average acceleration. In this particular case, our average acceleration is just 0 because we have a straight flat line. Again, we can consider the slope at a given point, or the slope of a tangent line, to be equal to the acceleration at that point for a velocity versus time graph. Now let's go ahead and graph our acceleration versus time when we have just a 0 meters per second squared. What we see is just a straight line, flat line across at 0. Note that if the velocity is constant, there is no acceleration, so we should see this flat line at 0. So let's consider the slope of a tangent line. Now here's just a generic graph of some curve. This could be a position versus time graph, or it could be a velocity versus time graph. But we can consider what the slope of the tangent line looks at a particular point in time. So let's pick the time 3 seconds. We draw in our tangent line, which will be a line that crosses the curve only in one location. And we can find the slope of that line, which is just going to be the rise over the run, or delta y over delta x. Let's consider the specific situation where we have a position versus time graph, so we can find the speed of the object at 3 seconds. Our rise, in this particular case, is 4 meters, and our run is 8 seconds. So we end up with the rise over the run being our 4 meters over 8 seconds, or 0.5 meters per second. Notice that the slope of that line is positive, so therefore our velocity is in the positive direction. So a quick summary, what we have done thus far is consider translating down. So we start with a position versus time graph. We use the slope to find our velocity at any given instant in time. We can then look at our velocity versus time graph and use the slope to find the acceleration. Now that we have considered translating down, let's look at translating up, meaning going from acceleration to velocity to position. Let's begin with looking at an acceleration versus time graph, where we have a constant acceleration of 4 meters per second squared. We can find the change in velocity by looking at the area under this curve, or in this particular case, this flat line. The area is going to be a rectangle with the base times the height being equal to the acceleration times the change in time. Note that a times t is our change in velocity. For this particular case, 4 meters per second squared times 3 seconds gives us a change in velocity of 12 meters per second. Now, what would that look like for the velocity versus time graph? First, we need to know what the starting condition is, meaning we need to know the initial velocity. Understanding that the change in velocity is 12 meters per second does not give us the final velocity or the initial velocity, just how it changes. We have to be given what the initial velocity is to be able to graph the velocity versus time. So in this particular case, let's just assume that the initial velocity is 0, it starts from rest, and accelerates at a rate of 4 meters per second every second that passes, so that after 3 seconds it is going 12 meters per second. We have a diagonal line because that change in velocity is constant, or the acceleration is constant. We will always be dealing with situations in this class where we have constant acceleration. Now again, we can look at the area under this curve to determine what the displacement is. So for this case, we have a triangle, so we're looking at half the base times the height. So half the velocity times the time gives us the displacement. Note that this particular case, we can just consider the final velocity as being 12 meters per second, and the time of 3 seconds times 1/2 gives us 18 meters. However, if it was a situation where we didn't start from rest, we could still look at that area under the curve to calculate the displacement. So we again have a constant acceleration of 4 meters per second squared, and we want to think about what the position looks like. Just as with the velocity graph, we needed to know the initial condition, the initial velocity to be able to graph the velocity versus time. We need to know the initial position to be able to graph the position versus time. Notice the curved shape of increasing slope. As time goes on, the object is moving faster and faster, and this shows up on our graph as a curve. So, in summary, we have this idea that we can go from an acceleration versus time graph to a velocity versus time graph by looking at the area under the curve plus needing to know the initial velocity. Then we can move from a velocity versus time graph to a position versus time graph by looking at the area under the velocity graph to plus the initial position to give us the position versus time graph. Let's sum up what we've done so far, and then we will do an example. So again, if you have a position versus time graph and you need to find the velocity, you use a slope. Or if you have the velocity and you want to find the acceleration graph, you use slopes again. So translating down, you use slopes. That is actually the first half of calculus, the derivative side of calculus. And if you want to go up on this little scale here, if you want to go from acceleration to velocity and velocity to position graphs, you use the area under the curve, the other half of calculus dealing with integrals. Now let's summarize this and then we'll do an example. So first, some steps for thinking about translating graphs. The first is that you will want to line up the x, v, and a graphs vertically with the position graph on the top. Break up the graph into any changes in motion. Also, you'll want to consider where the velocity crosses the the x-axis, I mean. And you'll want to start by graphing downwards tends to be easier. So if do any graphing downwards you can do, you'll want to look at slopes. If a slope jumps from one value to another, the graph will be discontinuous. Then consider any upward graphing you need to do. You'll want to place the starting point, which again, you always need to know what the initial condition is, whether that be going from an acceleration to a velocity graph, knowing your initial velocity, or going from a velocity to a position graph, knowing your initial position. Find the area under the sections. Now, you need to be careful about the signs. We gave an example where the velocity was positive. If you actually had a velocity that was negative, your line or curve would be underneath the x-axis, and you would consider from that curve up to the x-axis, and that displacement would be negative. You'll want to do a running total, placing a point at each of the correct for the times and for the total at that particular point, which I'll show you an example of in just a second. And then you need to consider whether or not to connect the dots with straight lines or curves. So here's an example. I have a velocity versus time graph with kind of two different segments that we'll want to consider. We are given that the initial position is -2 meters. I might suggest that you pause the video at this point and see if you can create the acceleration versus time graph and the position versus time graph. All right, let's take a look. So again, as I suggested, it's usually easier to translate down. So let's start with our acceleration versus time graph. In the first 2 seconds, we see that we're going to break this up into time segments. First 2 seconds and then the second 2 seconds. we see that the slope for those first 2 seconds is just 0. And for the second 2 seconds, we have a rise of negative 2 meters per second as it drops, and a run of 2 seconds. So our slope is negative 2 over 2, or negative 1 meter per second squared. So when we go to graph this acceleration, we see 2 segments of constant acceleration, one at 0 and one at negative 1. Again, in this class, we will always be dealing with situations where we have constant acceleration, so we will see this discontinuous acceleration pop up on our graphs, where you have just segments of straight lines, or flat horizontal lines. Now let's translate up. To translate up to our position graph, we need to consider the area under the curve. So again, we've broken this up into the first 2 seconds and the second 2 seconds. So for the first 2 seconds, we have this rectangular area, which has an area of 4 meters, 2 meters per second times 2 seconds. And then for the second 2 seconds, from time t equals 2 to 4, the area of that curve is 2 meters. So we can plot our points at, we begin at negative 2 meters. After the first 2 seconds, we have traveled a positive 4 meters. We go from negative 2 to a position of 2 meters. And then after the next 2 seconds, we displace another positive 2 meters. So again, notice that the area under curve gives you the displacement, not the position. So I've plotted my 3 points on the graph, and then I need to consider whether or not to connect it with straight lines or curves. For the first 2 seconds, we have a situation of constant velocity. That means that I should connect it with a line. For the second 2 seconds, we have a decreasing speed or velocity that is approaching 0. So we should see this as a curved segment where the slope of that curve is decreasing to 0. So this was your example of translating from position to velocity to acceleration, and from acceleration to velocity to position. We'll be doing more examples later. If you have any questions, please let us know. Thanks.